This talk will comprise of a couple different parts. We'll try to give you a little background on the CMOS image sensors and CMOS image sensor industry. Talk a little bit about Forza and how we fit into the CMOS image sensor industry. We'll talk a little bit about safety critical applications, which is sort of a very growing and upcoming part of the image sensor field. Some of the challenges that we faced and the industry as a whole faces in verifying image sensors, the methodology and flow that Forza uses and how Mentor fits into that methodology, and then we'll wrap it up and summarize the previous items. CMOS image sensor trends. What we've seen today is that the computerization of all things is very much impacting multiple industries, including those industries dealing with safety critical applications. From ADAS through deep learning and AI, we've seen a rapid increase in automotive sensors, especially CMOS image sensors, in both visible light and soon to be LiDAR imaging. Those are all systems that are very important, obviously, to a person's safety. The medical industry, with Obamacare and the digitization of medical records, has caused just a rapid influx of money and procurement of new equipment. And we see, in addition, AI and deep learning again affecting this industry with rapid turnaround time of analysis of pictures and data, as well as increased accuracy of analyzing those data. So the medical industry is rapidly just gaining more and more advanced CMOS image sensors and upgrading their equipment. Finally, although IoTs are not exactly safety critical devices, we see that because they're so prevalent and integral to people's lives, there's a security risk inherent to these products, a security risk that oftentimes can't be fixed after the product is shipped. And therefore, I'm going to label that under safety critical because when your security is compromised, we have problems. And we can see how the systems often being isolated and non-upgradable is particularly applicable to a lot of IoT devices. One thing that's driving a rapid adoption in CMOS image sensors is the advancement in the sensor technologies themselves. And as part of that, we see CMOS image sensor product lines in the fabs not enhancing or scaling geometrically as well as logic technology nodes. In order to take advantage of that scaling in the logic technology nodes, there's been a very rapid push for stacked sensor technology. And what we mean by stacked is the CMOS pixel array would take the top wafer or the top sensor, and that would be bonded in some form or fashion to a logic array at the bottom. And that allows us to achieve the best of both worlds, where you're having a great pixel array, large pixels, as much area use as possible to capturing light, obtaining great dynamic range, and at the bottom having very complex logic to be able to process or regionalize your data or ship it off at high speed, whatever the application may need. Image sensors as a whole have a couple of unique challenges due to the array-based architecture of the pixels. One of those is verification time and capacity, because it seems more often than not an image sensor is a column parallel architecture. What do we mean by column parallel? You have pixels. Let's take an HDR sensor with 1920 by 1080 resolution, 1920 in the horizontal, 1080 in the vertical. In a column parallel architecture, you would have 1,920 ADCs, 1,920 VLNs, and basically the entire readout chain is replicated 1,920 times. And that creates a lot of problems, right? If you want high accuracy, how's this verification going to be accomplished? SPICE model-wise, I mean, you're talking, again, how many, 1,000 transistors in these columns, and then multiplied by 1,920, that's just impractical. Likewise, there's a couple interactions that take place because a column parallel readout essentially means that these columns are all functioning at exactly the same time. That introduces sensitivity to crosstalk. That includes problems with device matching, parasitics, the interaction. Let's say we have a 4-micron pixel. Your columns are essentially 4 microns wide, and that's how much space your ADC has to fit. So if that ADC is operating next to another ADC, depending on how the value of the signal coming in, the conversion rate could be different, and that interacts with the nearby columns and causes issues. So there's a lot of unique problems to this type of architecture, which causes us to come up with a couple different methodologies to best solve them. And just to show you a little graphic of what we mean by column parallel architecture, we'll zoom in really quick on the pixel array. So here you can see a small caricature of what the pixels look like in the array-based format with a single vertical readout line going to a amplifier and a select switch. And the charge travels through all these columns, all these rows in one direction. So we have to be careful as far as the routing goes, even in the pixel array itself, that we don't instill any operation that would cause that voltage level to move around while the readout process is occurring. Now I'll talk a little about Forza. So Forza Silicon, headquartered, is in Pasadena, California. We've been there since 2001, so for 17 years. We have over 45 employees, a large portion of them engineers. We work with a lot of different foundries, over 25 in our history. And I work personally with many different PDKs at any given time. So it's a very constant struggle to satisfy the engineering requirements and then accept new projects from whatever our customers would feel best on as far as a technology node and foundry. We've done many, many designs, so 200 plus mix-and-load designs over the last 15 years. And if you look at the cumulative years of design experience of our employee base, that's averaging about 10 years in engineer. So I would say that I've been with the company personally 12 years, and I think many of our employees have been around for 10 years or more. So that speaks a lot for the culture and the strength of our company, I think. 80 plus core patents, those are both from inside the company and cross-licensed with nearby companies like JPL, Caltech, and others. So we make sure that we don't have any issues designing the latest architectures for our clients. And finally, long-term relationships, big and small. We work with customers of all sizes. And if I didn't state before, our company is a mixed-signal image sensor design house. So we do not have our own products. All of our products are design services, IP deliveries to our customers. The diverse customer base and applications that we do image sensors for include these above, like automotive, high performance, still and video cameras, industrial, medical, military, and IoT. But for the purposes of this talk on safety critical designs, we're gonna focus on automotive and medical, but we'll do a little more deep dive on the medical side. Some of the designs that we produced here include this design to the left, a 1.2 megapixel stereoscopic image sensor with a coprocessor. This is, I believe, the first gen design of this chip used in a surgery type application. And we'll do a little more deep dive on that later. The second sensor, HDR Automotive, that I believe is a 130 dB dynamic range sensor for backup camera. We also have a much larger high resolution CMOS image sensor, 163 megapixel, and that runs at 20 frames per second full frame. And finally, this is the most unique and, in a sense, my favorite sensor at our company. It's this 2-pixel sensor, and people think, what are we going to do with 2 pixels? Well, this application is very unique because it's a glucose monitor. And one would think, how does a chip monitor glucose levels through a visible light sensor? Well, the company who came to us with this design decided that they were going to use the protein, a protein at the end of a small endoscopic needle, and that would be applied to your skin so that this protein will give a bioluminescence. And you can imagine how small of a light you're going to get from that one protein. So these pixels in this chip are about 400 microns square, and that's just, humongous. But whatever it takes to fit the application, and also uniquely RF link on board. So most foundries, when they ship a image sensor technology, it's quite limited in the devices that are available because it tends to be a cost-sensitive process. In this case, we were able to convince the foundry to give us both the cost-sensitive devices plus some RF nodes in order to have both on the same chip, and that was very great when we got that back in the lab and were able to communicate with it over Zigbee. Just to show you a couple of the foundries we work with, quite a diverse set, and again, we try to choose the best foundry that provides the cost, the capabilities, and if they need onshore or offshore, capabilities, that's who we work with. And across a wide variety of technology nodes, all the way currently from 180 to 40 nanometers. One thing Forza tries to do to accommodate all of our customers is traditionally we've done design services, starting from the architecture study down through tape out to foundry. But we've seen that a lot of systems level companies are very interested in trying to obtain a very unique sensor to fit their application space. And in order to do that, they want to focus on the system level design and not worry about the production service as part of receiving a good product. So you can see here that we've now have what we call a value plus or a turnkey flow available, which can allow us to do the prototyping, probe development, yield optimization, qualification, and test and delivery for our customers. And that's great for both our customers and us because you're going to get a production quality tested design delivered to your doorstep and packaged. And then we get to have that yield learning involved so we can feed back with all of our dedicated engineers who helped design that chip to feed that, test data back into the development cycle for a future iteration or future designs. So what are the safety critical applications of medical imaging? We see that, first of all, medical imaging encompasses a number of different players. The image sensor or component makers, subsystem developers, and then the equipment makers. So there's quite a large number of players involved here. The market also is a really big pie of money. And we see that from the IC developers, we're looking at around 350 million in sales a year. The solid state, 3.5 billion, 10x more, and then 10x more, 35 billion in the equipment makers. So we think that this market has a sizable amount of revenue to be tapped into. And we can see that given all this computerization of devices and technologies in the market, that the CAGR index up to 2022 shows a pretty healthy growth potential from the IC level around 8.5%, and from the equipment market about 5.5%. So I think this is a good place to be. From a medical imaging point of view, we see that there's a variety of sub-application spaces involved, anywhere from X-ray to ultrasound imaging, all of which require different architectures in the design. And interestingly enough, I was asked a question earlier about X-ray sensors. It's like, well, how does a image sensor, which we think of as a visible light sensor, detect X-rays? And we see that due to the sharing of knowledge between application spaces, X-ray sensors actually have something called a scintillator on top, which takes these X-rays, converts them into visible light, and then that's what hits the sensor itself. So at the end of the day, what we see as a company is still a visible light image, but we're receiving X-rays through this scintillator conversion. So I thought that was very interesting, and I wanted to share with you. So how does this apply to us as people using the medical technologies? We see that people, or the industry is going towards this sort of small incision or endoscopic type of surgery because that is the least invasive to a body. And we don't want to have like these wounds that take months to heal anymore, right? We'd rather use technology to help make the medical surgical process easier. So this, in order to obtain this technology at a high level today, at a very technical level, we are trying to computerize it by adding these image sensors with very low light sensing capabilities. We also see that for non-invasive, monitoring of your esophagus, there's these capsule endoscopy methods, which are a complete system, kind of like our glucose sensor was. It's a single capsule with batteries, with an imager on board. There's a light, and it will last maybe 24 hours, but you have this sort of wristwatch on your arm, which is going to receive the RF signal from that device and record it, and then your doctor in the future will be able to, play that back and get a full image of your digestive tract. And finally, the robotic surgeries are a big deal these days, because how often does it occur that maybe you want to use a specific doctor, a doctor that specializes in one particular field of surgery, and that doctor is not present at your hospital. Well, we have this telepresence now that's occurring with high-speed internet and the advancement of stereoscopic image sensors. So now the doctor can be another country away, and he can still give you the best care and the best surgical procedures available remotely. So one detail, as I mentioned, about robotic surgery is that it requires the user, the surgeon, to have a depth perception of the patient. And to do that, this stereoscopic imager technology, which you can see left eye, right eye from the perspective of the surgeon, allows them to do. And that was present in the sensor example I just showed. So what are some of the challenges in verification of these sensors? To use a particular test case, this stereoscopic robotic sensor, just some specs here, but 1.7 micron pixel, it's pretty small, 60 frames per second. We want to have real-time speed for that surgical process. And it's using some of the most advanced nodes that are available, 65 nanometer BSI imaging process, and a little bit cost sensitivity for our customer, 90 nanometer for the logic portion. Just to give sort of like a more technical overview of this, what we have here, again, split into the left eye and right eye pixel arrays. In this case, this is the second generation design of this product. There's TSVs on board, and most of the logic you see on the logic wafer itself, and that includes VLNs, ADCs, SRAMs, and then this sort of common digital block, which does other processing to the data before reading it off the chip in the CML logic. So what do we do to ensure that the readout chain is functioning well? Well, we have a number of test injection points. So this sort of caricature here shows the flow of the data through our column, but we try to inject test signals at most stages of that processing. And that allows us to both functionally verify that every stage is performing correctly as we expect, and to troubleshoot issues as early on as possible. Because once you inject, say, at the pixel level, and now you have all these variables introduced in the design simulation phase, it's hard to debug. So we want to make sure we provide that test injection points at most all stages of the analog column readout chain. And here's one between the VLN and sample and hold that I will talk a little more in detail on in the next few slides. And just for those interested in more of like a technical caricature of our readout architecture. Here's another slide just showing how there's 2 transfer gates in our pixel, and we have the VLN that can be enabled or disabled depending on if the test injection mode is enabled or not, and sampling caps, preamplifiers, comparators. We have latches in front of our SRAM, things like that. Oops, sorry about that. Yep. Well, okay. So what I wanted to show in the previous slide was that our digital readout chain basically comprises of an 8-bit, 10-bit serializer and a serializer to get the data off CML. Some of the challenges, as I sort of elaborated on the first slide, is because we have 2 competing sort of demands here. One is that we want to have a full high-precision validation of our entire sensor array, including those device mismatch effects, including those crosstalk and parasitics, and including like high-accuracy ADC conversions. But at the same time, having 1920 of those in parallel makes it virtually impractical to do a full SPICE level sim. So what are we going to do in our methodology to try to have a great accuracy but make sure that we cover all our bases? We also want to make sure that from a functional point of view, we cover all modes of operation, and the more logic the sensor has, the more operating modes it will probably have as well. So that becomes a problem the more advanced the logic becomes in these image sensors. And finally, where does mixed signal come in? We have to make a decision as a company to what parts of the design can we sort of put into in a Verilog code, Verilog D code, and what components can be in full SPICE in order to achieve not just the accuracy we need, but the coverage we need. So the flow at Forza. Essentially, in a very blunt summary, is as this: pixel characterization and device noise analysis we do in full SPICE accuracy using the AFS simulator. And in addition, the signal chain characterization, both in a singular and in a multiple, also using full SPICE accuracy AFS characterization. In those cases, when we tend to do an RC extracted view of those to obtain these crosstalk interactions, we can use some advanced features of AFS like parasitic reduction, high performance mode, and things like that to input the maximum frequency of our design and then cut out all those parasitics which may be too small to impact our design but would heavily impact the runtime of our simulator. And next, lastly, we have these functional or timing modes. In this particular test case, which I'll be talking about, there was a row injection mode and an imaging mode. The row injection mode I kind of elaborated on earlier is injecting a test signal just after the VLN before the sample and hold logic. And in image mode, we actually inject a signal at the pixel photodiode itself, and then we control the pixel as normally to read out our signal throughout the entire signal chain. And that's done through the analog fast SPICE mixed signal platform, next generation mixed signal platform specifically. The test case details here, I can just briefly say, this both analog and digital. What we see as a company is that the digital block does not need to be simulated in SPICE. It's very, very functional, and we do get timing data from that functional code based on the clock coming into that digital block. So that does not need to be simulated in full SPICE accuracy. As well, some circuits are impractical to include because of the massive amount of time steps they generate during our simulation, like the LDO, reference generators, and PLLs. So from a pure functional perspective, we're checking 2 things. We're checking connectivity, making sure all the signals from the digital code, the digital block, are wired correctly to our road drivers and the analog column, as well as timing, making sure that the clocks going into both blocks are timed correctly and all that signals propagate through the chain correctly. You can see that there's also a number of boundary elements, and those boundary elements are generated by the next generation mixed signal platform between our digital Verilog code and the analog domain. So there's quite a few signals, control signals in between those two domains. To show the setup from a more batch mode sort of level, we can see that this next generation mixed signal simulator, which here is called Symphony, is essentially a wrapper between an analog simulator and a digital simulator. Currently, it supports AFS as the analog simulator, and it supports multiple digital simulators. So each company doesn't have to migrate particularly to the Mentor digital simulator flow to make this work. And what's great about this wrapper is that it kind of leaves the original simulators alone. So your analog simulator can continue using the analog switches that you may be familiar with. And likewise, the digital simulator can continue using all those digital switches which the digital designers may have ran their test benches on. And so you have this kind of feature parity for the people running the top level sim, whether it be analog or digital designers. They have very little to learn because they can just copy the code from the other domain, whether it's analog on top, copying the digital switches, or digital on top, copying the analog switches. So one thing I really appreciate about this flow is just the ease of use. It simplifies my time. I made a comment that in previous flows for mixed signal, I had to write a wiki page, internal wiki page at our company, and that was basically 3 pages long worth of instructions that in case A do this, case B do this for a mixed signal sim. And to this day, when we use that old flow, the engineers at our company still need to reference that page because it's just so complicated. But with this flow, especially on the GUI side, you can just click 2 buttons and you're almost ready to run. And that just saves me and saves our engineers every time they run a mixed signal sim a load of time. So I really appreciate that. Lastly, at the bottom, I didn't mention, but there's a connect view that sort of joins the analog and digital domains together. So in that, we specify, in this case, it's an analog top level. We specify each of the blocks in that analog top, which are digital. And then at the very last line, sort of what voltage level those will be switching at. From the GUI side, it's very simple again. You have a schematic database test bench set up. The digital guys provide their digital HDL code, which you can either keep a separate file or you can import into your mixed signal sort of schematic capture flow. And then in this particular case, the images are from the Virtuoso tool. So we use the config viewer HED to specify which blocks are analog and digital. And then the AMS ADE environment here, also from the Virtuoso flow, is very simple. It's exactly the same that our engineers use for a pure analog sim. So really, there's very little differences. Again, very little setup. In the bullet points below, we see that there's a BE setup, which is what, again, was this boundary element. We're using 1.2 volts here. And then we may set such things as run control or what level of hierarchy we want to capture or save signals in the digital domain. Again, all very straightforward for our engineers who use this flow. The waveforms can be viewed in either the native waveform viewer or the Mentor waveform viewer called EasyWave. And one thing I appreciate about what Mentor is doing here is the EasyWave tool allows you to import both the digital and the analog result files and stitch them together essentially in one waveform view. So previously we had the analog guys popping up the digital waveform viewer alongside their analog waveform viewer and trying to cross-reference signals at different time points and such. And that kind of left room for error. So with this particular EasyWave waveform viewer, we can now see both domains stitched together in one place, and that just makes it much easier to debug, to create screenshots for any design reviews, things like that. And finally, for me as CAD, I love to be able to help our engineers debug problems. And Symphony provides a lot of output to do that. Besides just the native tools, analogs output and digital output, we see this joining together through the boundary element code outputted very cleanly to a log file, so we can tell if maybe a boundary element didn't get captured correctly, or if it was set wrong. Maybe we had a digital block in this design that was 1.2, but there might have been an IO level 3.3 piece of digital code somewhere, and it was not set properly. So all these log files are very easy to look through, very easy to debug. Something I continually hammer our engineers, like, hey, before you tell CAD, look at the log file, and it's starting to work. So appreciate that. Just to show an example here, so we have this row injection test case, and we're putting a signal on the VLN, after the VLN, to the sample and hold. When sample pick switches high, we capture that signal on the sample and hold capacitor, and then that gets converted into a signal through Pixel LE and Pixel RE. Now, because these are supposed to be symmetrical, what we're looking at here is just the sort of the matching of the signal conversion between the right eye and left eye. And without overlapping them, we can basically see that they're doing the same thing. So that is already a good sign for us. And by the way, all these signals are controlled by, again, the digital control logic. So the timing of the row control signals, the timing of the ADC conversion, all that's done through the digital block. And we can see that that is functioning normally here. Just to give a little more detail about the second half. So we got through the end of ADC conversion at that first slide. Now here we're going to see the SRAM inputs and then the pixel outputs. I know it's kind of blurry, but basically the point of this is that what's coming out of the SRAM after it goes through the 8B10B logic and the serializer and the CML needs to come back through our RX checker and show that the values of that data is identical. And that proves to us that the data went through the system correctly. And again, I know a little hard to see. We see that the 1DF655 pattern comes out at the left eye, and as well the 1E1000 pattern is repeated on the right eye after the RX checker. Test case, we ran a number of different top-level designs with this next generation mix-signal platform. And in pretty much every case, we saw some improvement to 1.4x improvement. And again, like from these generically long-running sims, any type of improvement we can get is just really appreciated by our designers. So we're happy that not only do you get better ease of use, better debugability, but we also get faster runtime. So in summary, we learned a little bit about the image sensor market, how rapid computerization, digitization is causing an influx of new designers, new customers, new ICs in this field, and Forza is happy to be a part of it. We also have been doing CMOS image sensors for 17 years, and it's great that the industry is growing, and we're happy to be here and happy to support anyone who wants to get into this space. The CMOS image sensor verification has always been a challenge from day one, but now with safety critical designs, even more so to capture all the test cases and make sure we do that accurately and at high performance. And finally, the way we addressed it today is using the next generation mixed signal platform from Mentor and AFS. And with that, I thank everyone for coming and thank the team at Mentor for all the support they've given us.